Why can't Webb just look at all known exoplanets? How much science will Dragonfly do? And when's the next Gaia release? And in Q&A Plus, what does Q&A Plus actually do? All this and more in this question show. It's time for the question show. Your questions, my answers, as always, wherever you are, across my channel. If a question pops in your brain, just write it down, I'll gather them up, and I will answer them here. Now, obviously, I am not back at home. I am in Japan right now, finding some quiet alley to be able to record the intro to this question show. So the intros are going to look very different from the rest of the episode. All right, let's get into the questions.
Eagle Hornblower, I'm curious, how much science can Dragonfly really do? If Titan's surface is just water ice, what kind of geology of interest is there? So the rocks on Titan, the mountains, are water ice. The sand on Titan is water ice, but there is an enormous amount of organic molecules mixed in with that. I mean, we know that at the northern latitude, there are lakes of methane. It rains methane. There are seas of methane, rivers of methane, and clouds of methane. But you're going to have a lot of organic material on the surface of Titan. We saw just these really interesting pictures that came back from the Huygens probe as it was entering the atmosphere. You could see the landscape of Titan, and then it landed on the surface, and you could see this bizarre surface with these weird little rocks on it made of water ice. And so like purely like if you're not interested on the biological side and you're just interested in the geology side, that alone is reason enough to send a helicopter to Titan. You're going to be flying around. You're going to be seeing what sand dunes do on Titan. You're going to be seeing what the layers of rock, seeing ancient impact craters, and all of that is going to be really interesting to geologists. But then to chemists and astrobiologists, you're also seeing the interactions between these organic chemicals on the surface of this planet and how they're interacting with the very thick atmospheric haze. So there is no shortage of science that's going to be done from Titan Dragonfly. And I think, you know, with all missions, often we don't know. Well, we don't know. We don't know what is going to be the exciting thing that people are going to be finding there. That once we actually arrive, and there's a bunch of science goals that the scientists are attempting to achieve, then they're going to find something new, something totally unexpected that is going to sort of revolutionize our understanding about Titan. And you only get that when you have boots on the ground, or in this case, a helicopter in the air. So yeah, absolutely worth sending a helicopter to Titan to learn more. King, why can't Webb just rush through all the closest exoplanets and determine their atmospheres? What is it there that's much more important? They are trying. You know, the question is, how much time do you spend with Webb on an exoplanet? What if you spent all the time? What if you spent weeks and weeks and weeks of James Webb time and you weren't able to determine the atmosphere to the level you were hoping? So what happens is, you know, there's only one great system that Webb is able to observe and give us a really good answer about whether or not they have atmospheres and are like Earth-sized worlds orbiting around red dwarf stars. The system that I'm talking about, of course, is the TRAPPIST-1 system. This is where you've got 7 Earth-sized worlds orbiting around a red dwarf star. Several of these planets are located in the habitable zone. It is relatively close to us compared to all of the other exoplanets that have similar characteristics. Like we know of a bunch of red dwarf stars with Earth-sized worlds orbiting around them, but the TRAPPIST-1 system is the one that is the closest and the best. It is the gold standard for being able to do this work. And so most of the time that Webb has been allocated for observing potentially exoplanets' atmospheres on Earth-sized worlds is at the TRAPPIST-1 system. And the work has been really, really difficult, very complicated. And the problem is, and this is something that we've talked about this in Space Bites. I've done interviews about this. The problem is that the star has a lot of variability, that you've got granules and flares and coronal mass ejections and just small amounts of variability. They call this pollution of the signal. And so you're watching the planet pass in front of the star and you're getting all of this variability and pollution that's coming from the star that makes it really difficult to figure out whether or not there's an atmosphere. And originally, astronomers sort of had this overly simplistic idea of how hard this was going to be. They were expecting we're just going to turn James Webb on, look at the TRAPPIST-1 system, we're going to wait for the transits of the different planets, We should detect no atmosphere around the closest one. It'll be like Mercury. We'll detect an atmosphere around the next one. It's going to be kind of like Venus. Then we'll detect a bunch of Earths, and then who knows what comes next. And instead, they didn't get a clear signal about whether or not there's an atmosphere. There's probably not an atmosphere around the first two planets. They don't know if there's an atmosphere around the third one. Maybe not, but some people think maybe. And so as long as you have this inconclusive sort of level of data, then people are going to have these arguments about it. And so there's no reason to believe that more Webb time will get you what you need. But we have reported on some papers that have proposed, like, what is the number? And that you probably want like 9 transits of a planet, both across the front of the star as well as going behind the star. And that's a lot of data. Like, it's a lot of time that you are going to be tying up James Webb to watch all those transits, to steer back, to look at the TRAPPIST-1 system while this transit is happening, gather a lot of data. You have to watch transit after transit after transit to build up this picture, to even detect the presence of the atmosphere. And Webb's got a lot of jobs to do. It is trying to figure out what the first billion years of the universe looked like. It's trying to understand how the building blocks of galaxies came together. It's looking at objects within the solar system. It's got to check when interstellar objects pass through. It has a very busy schedule, but there is a lot of time in every cycle that has been dedicated to the TRAPPIST-1 system, because that is the best chance. And if they find it at the TRAPPIST-1 system, then they can go and look at some other red dwarf system and go from there. But yeah, it's just, they're throwing tons of time at it, and it's still not enough for them to get a conclusive answer. And it might be that we need a different telescope. So the European Space Agency is launching a telescope called Ariel, which is in 2029. And that is specifically only going to be looking at exoplanetary atmospheres, although it's going to be looking at lots of different kinds of planets, hot Jupiters, mini Neptunes, things like that. And then you've got the recent Pandora telescope that just launched. And the same thing, it's going to be looking at 20 exoplanets, measuring their atmospheres. And it's going to put in, like, it's going to make 10 observations of each one of these planets every year and do like 24 hours of observations on each one of these planets over the course of the first year. And it should operate just year after year after year. So it might not be that James Webb is going to be the right tool for the job. It is a Swiss Army knife. It can do a lot of stuff. It is the greatest telescope that humanity's ever built, but it is not the best possible instrument that can be imagined to do the work of examining exoplanetary atmospheres. It might just need to be a better spacecraft to finally launch. That will probably be Ariel in 2029 to 2032.
It's time to shout out our new patrons at the $5 level and above. Stephen Williams, Phil, Robert Payne, Russell Quarles, Arthur Adelberg, Michael Traz, Eric Starbuck, Brian Chalhorn, Sean, and Suzette. Join our community at patreon.com/universetoday.
Nunya, from a technical standpoint, is there a maximum amount of time which James Webb can focus on a single target? Like, technically, no. You've got the orbital mechanics. So James Webb is orbiting at the Earth, Sun, L2 Lagrange point, and it has access to the sky, except for the stuff that is blocked by its sun shield. And under the sun shield is the Earth, the sun, and the moon. And so it can't look in that general direction, because then it'll be blinded and the temperature will go off and it won't be able to do its job. And so instead you have to wait 6 months for Webb to come all the way around around the sun with the Earth, so that now the other hemisphere of the sky is available to it and can make all those observations. So, but it can hold fast on a target for incredibly long periods of time. It hasn't needed to. The crazy part about Webb is that they've gotten observations that are equivalent to the Hubble Deep Field, which took hundreds of hours of Hubble time. They can do that in a couple of hours with James Webb, and have. And they have done more. I mean, there have been some long observations, some accumulation of observations that are much deeper, much more sensitive than the Hubble Deep Field. And we're still waiting for, eventually in a couple of years, all the different survey groups will come together and they'll agree on what will be the James Webb Deep Field. And then they will do the equivalent of Hubble time, hundreds of hours on some spot in the sky, and just go right to the very edge of the observable universe, which would just be amazing. So really, you're limited by the parts of the sky that are available to you with James Webb at the time of the year. But this is kind of the same constraint that any astronomy has to deal with. That, like, right now, I can go outside, and we're just entering the beginning of the summer constellations. Jupiter is just, back in December when I would go outside, Jupiter was just peeking over the mountains in the evening. And now Jupiter is just about to set every night. So I go outside, I can look at Jupiter for an hour, and then it sets. And so you're always limited by which objects are up in your night sky at the time. And that even is the same when you're out in space. One hemisphere is available to you in the sky, and then the other hemisphere is crowded out by the sun, the earth, and the moon as very bright objects. Earthling Fire. When can we expect Gaia data release 4, and are we still expecting it to provide thousands of exoplanets? So Gaia has released 3 data releases so far, and data release 4 is due for June 2026. So we are just about a month and a half away from data release 4. It'll be a sort of the provisional early sneak peek version of it, and they'll continue adding information to it, and then they'll solidify data release 4, and they'll move on to data release 5. There are dozens of exoplanetary discoveries in the previous data releases, and so there will be more exoplanet information in data release 4. I don't know if it's going to end up being thousands of exoplanets. I mean, I've heard estimates that there could be anywhere as high as like 10,000, 100,000 exoplanet discoveries in the full Gaia release, but we're going to have to wait for the final data release 5, which will probably be close to the end of the decade. And then we'll know how many exoplanets Gaia was able to find. But it's great because it uses this astrometry method. The different methods, the transit method and the radial velocity, require the star to be aligned with the planet. But astrometry, you want to be able to see the system at some angle or face on. And then you're watching the star make this little shape in the sky. Gaia was watching all of these stars and watching them all make little spirals. And then from that, it will have been able to calculate the planets that are orbiting around them. But it was never sort of fully intended to do that. Like it was designed to detect the motions and the positions of all of these stars. It was able to detect exoplanets causing these little wobbles around their stars, but that wasn't its primary scientific objective. So the fact that it can do it is just because Gaia is amazing.
Did you know that you can watch the same video with no ads and get a bonus question over on Patreon completely for free? We call it Q&A Plus. This week's bonus question, what does Q&A Plus actually do? I'll put a link in the show notes. All right, those are all the questions that we had in this episode. Thank you, everyone who asked your questions in the YouTube comments, everybody who joined me for the last live show that I did just before I left for Japan. So thank you, everyone. Now, I'm going to talk just about traveling in Japan. But first, I'd like to thank our patrons. Thanks to Abe Kingston, Andrea Pedretti, Brian Bodie, Caradwin, Chuck Hawkins, Commander Baylock, Dirk Fingett, David Gilton, David Matz, Enthralling Reading and Math for Toddlers, Eric Lindstrom, Evan.Pro, James Clark, Jerry Matter, Jim Burke, Jordan Young, Josh Schultz, Marcel Sitz, Michael Purcell, Nordspace, OneSipForAnimals.org. Please follow my nephew at vbrick6994, Ren Kaidu, Richard Williams, Sean Sargent, Stephen Fallon Munley, Team 49, Telescopes Canada, Vlad Chiplin, Wolfgang Glutz, and Zeldemort Galactic Defender, who support us at the Master of the Universe level. And all our patrons, all your support means the universe to us. So once again, I am traveling in Japan. Now, those of you who are fans of the channel might remember that I did this 2 years ago with my son, and this was sort of his dream location to go and travel in the world, and it was amazing, and we had a great time, and it kind of really opened up both of our eyes about this whole part of the world. And I came home and was raving about it to my wife. And she's like, well, when do I get to go to Japan? And so that time is now. And so I am sort of retracing roughly the route that I took with my son, doing Tokyo, Kyoto, probably Osaka, not sure, and some other places. And then we will be back in about a week. And it's a wonderful, wonderful place. It's definitely busier than it was. I think when we were here a couple of years ago, it was like just about a year after the COVID had sort of settled down. And so there was a lot less travelers and things were a lot easier to get into. This time around, I can feel what sort of normal tourist Japan probably is more like, and it is definitely a lot busier. Streets are very crowded, but still, it's an incredible place. And just this place where, because so many people live so close to each other, they have to be able to be efficient and disciplined and considerate of everybody else's needs. And it's just a really kind of wonderful place. And I enjoy the food and all of the anime references and everything. So it's great. So if you're ever, and I think, before I came to Japan the first time, I really sort of felt like it was going to be a really difficult place to travel in. I didn't speak the language. It's just a totally different culture, beyond like, sushi and you watch the anime, but you don't really know what it's like. But it's such an easy country to travel in. Everybody is so polite, so nice. Everything is available in English if you need it. The translation apps are there. You can use Google Maps to organize and take yourself around. And the prices are very reasonable. Unfortunately, their economy has been stalled for quite a while. And so you can find your way around Japan and really experience the culture and the food and just everything there is to see. And I put it up there on the list as one of the best places to travel in the world. Next time, I want to do this for business. Next time I want to come back and go to Jackson and go watch the rocket launches and things like that. But I'm still sort of scouting out and getting my sea legs. All right. We'll see you next time.